Hello, planetary students. It's just about time for exam two. And so I'd like to go over what you're going to need to do to get ready to do well on that. First off, remember that the exam is only available the first part of the week. So it'll be very similar timing to what we had on the for the first exam. And so make sure you get it done early so that you can so you can do the assignments in the second half of the week as well. Now, this exam is going to be a very similar format to the first exam. It's going to have the same kind of approach. So there are going to be 10 multiple choice questions, and then you're going to have a set of written answer questions. The exam will be set up as an open book exam, just like the first one. And just like the first one, that means you really should, though, study for it like it's a closed book exam. You will be needing to do that. You don't want to spend the entire exam time just looking things up. So get yourself ready as if it was a closed book exam, and then if you need to look things up, you can, but you're not having to rely on that all the way through. So the make sure you also look at the exam review sheet. That really runs through in much more detail exactly what it is going to be covered here. There's a study checklist on there, and that helps you prepare for the exam. Reminds you what things we've covered and what are what things you want to make sure you're practicing here. And you'll notice on that review sheet, a lot of what it says is practice. Um, with these assignments, with these exams, um, doing the assignments, redoing the assignments so that you really are comfortable answering those questions uh, makes a huge difference in being ready to do the exam. So let me just remind you about the format. There are going to be a set of multiple choice questions. As I said, there'll be 10 of those, and they'll be covering material since the last exam. So starting with matter and light and running right through surface geology. Then there will be the three written answer questions. The first one is a review question. This is one that asks you to review the material that we've covered, going through, and particularly it'll be very similar to some of the note-taking questions. You'll find that there is a set of selected answers to selected note-taking questions on Canvas, so make sure you take a look at those. One thing you may see on the review question that I give you on the exam is that I might give you some pictures that were in the online lecture and ask you to tie what you're saying to those pictures. So make sure you're doing that. Make sure you recognize, you go back, have a quick look at those lectures and remind yourself what the visuals are that go with them. There'll then be a critical thinking question. This would be like some of the your turn or mystery solar system questions that we've done. Um, and these are places where you're applying the ideas from the review questions. So um, I might give you a planet and have you talk about its formation, or talk about the way light and matter interact in a simple system, or look at what kind of surface processes are likely on a planet. So you've done several questions like this now, and there'll be similar types of questions to what you've seen. And then finally, there's a calculation question. And this again will be based on a mystery solar system data table, and it'll be the kinds of calculations we've done before. We've done three different calculations here since the last exam. We did the Wien's law calculation. That's where you calculate temperature. There's the density calculation, and finally, there's the escape velocity calculation. And so you'll get one of those three. So make sure you practice those. Make sure you know how to get an answer on one of those questions. So let me then run through some of the key ideas that we've talked about since the last exam. And the first chapter that we were addressing at that point was the matter and light chapter. That's the one where we looked at the basic properties of matter, and that includes the structure of an atom. So you should be able to think about, okay, what are the parts of an atom? What are they made of? How do those parts relate to each other? Um, and we also talked about some of the bulk properties of matter, especially things like mass, volume, and density. And as you've seen, density is a really important one, right? Density is what tells us what a planet's made of. So understanding that and understanding the distinctions between those three terms is going to be really important here. So on the light side of this, we talked a lot about the different types of light. And you should certainly be familiar with those different parts of the electromagnetic spectrum: radio, infrared, visible, ultraviolet, X-rays, and gamma rays, and have a sense of how they relate to each other. We've also talked a lot about the interaction of light and matter, okay? Matter can absorb light, matter can reflect light, matter can transmit light, and matter can emit light, that is, create light itself. So you want to have a good sense of what each of those terms mean and where they're happening at any given point. One particular way that light gets emitted is thermal radiation. And so remember, thermal radiation is the light something emits because of its temperature. And so the hotter something is, the more light it emits, and especially the more light it emits at shorter wavelengths. And so we took advantage of this. That was the Wien's law calculation, and we can use that to determine the temperature of a planet just by looking at the light that it's emitting. So those are a lot of the key points, the most important things that we talked about in that matter and light chapter. And that really marked the end of the physics part of the course too. That was the last big topic in that part. And we got to shift then into dealing with applying all those physics ideas to the objects in our solar system. And so the next chapter was the solar system chapter. And in that chapter, we looked at our solar system and we looked at it a couple of different ways. We talked about individual planets, but also we looked at them in groups and saw how they relate to each other. So we have the terrestrial planets. Those are the small rocky planets in close to the sun. And then we have the Jovian planets, the big, low density, the fluffy planets that are out in the outer solar system. But again, don't get thrown off by saying they're fluffy. They are lower density, but they still have lots of mass. There's a lot more material in those Jovian planets. And so you want to have a reasonable sense of what each of the planets in our solar system is like. But you also want to be able to want to know about the distinctions between the inner and the outer planets and how they relate to each other. You also want to look at the other big trends that we talked about in our solar system, not only the two different types of planets, but also how the planets move, right? They're all moving around the sun in the same direction, in the same plane. And most of the other stuff in the solar system is doing the same thing to more or less extent. So that's telling us something important about the way our solar system was put together, right? It's telling us that that direction of motion was very fundamental to the way the solar system formed. The fact that there's lots of small bodies, it's not just the planets, there's a lot of little stuff. And then there's some weird things. There's some exceptional bodies that don't seem to fit those patterns. And so you want to have a sense of what those are in the solar system. Um, we also talked a little more about the small bodies in our solar system and some of the things that make the small bodies distinct. And when I say small bodies, I'm not just talking about small planets. I'm really talking about things much smaller than planets. I'm talking about things that are like a small asteroid or a small moon. And that includes things like that they have very irregular shapes, okay? They're not spheres. They're often not held together very solidly. They're of course going to tend to be very heavily cratered. They're not going to have atmospheres. So these are some of the things that distinguish the smaller bodies from the bigger ones. And we looked at the major groups, the asteroid belt, the Kuiper belt, and the stuff way out there, the Oort cloud. Okay, so then we looked at exosystems, and that means the systems of these are the planets that orbit around other stars. And a few key points that we learned about those. First of all, there are several different ways of detecting them. They're not easy to see. And so while direct observation is one of those, it's by no means the most common way of finding exoplanets. Normally, the way we find them is indirect methods. Okay, and we looked at two of those. We looked at the wobble method, that is the radial velocity method, and we looked at the transit method. And so in the wobble, the planet makes the star wiggle back and forth a little bit, and we can see how the fact the planet is there, not because we see the planet, but because the star is being moved by the planet's gravity. And then there's the transit method, where again, we don't necessarily directly see the planet, but we see that the star gets fainter because something passes in front of it. And it's the presence of that object passing in front of the star that tells us, there's a planet there blocking a little bit of the light. And so those two methods, along with direct observation, each have different strengths and weaknesses. They are each tell us different things about the planets that set themselves in terms of things like radial velocity tells us about mass, but the transit tells us about size, about volume. They all tell us something about how far the planet is from the star. But they also have what we call selection effects, biases. There are certain kinds of planets that they can find more easily. So, of course, bigger planets are always easier to find than small ones. That's going to be true for all of these. But radial velocity and transits, they're really both much better at finding planets that are really close to their stars, while the direct observation is really best for finding planets that are far away from its star. So those are some of the kinds of things you want to be looking at for that uh, for that exoplanet section. Next, we talked about solar system formation, and again, those big trends came in terms of how we develop our model of how the solar system formed. But the key thing that you want to be thinking about here is the steps in the formation process. And you want to really feel like you got the sense of what are those steps that go into the formation process. You start with a great big cloud of gas in the ISM, and it contracts under its own gravity. Its gravity pulls itself together into a star and a disk. And the disk forms because there's a little bit of rotational motion there. And that little bit gets magnified as it contracts until a lot of the stuff is actually orbiting around that central star. So that's how the solar system as a whole starts to form. And then within that disk, interesting stuff starts to happen. First, the materials start differentiating by temperature. That is, some stuff forms solid. Okay, it condenses. Other stuff remains as a gas. And so, depending on where you are in the solar system and what the temperature is, you get different materials that become solid. So, in close to the star, the only things that can stay solid are the rock and the metal. So that's that's the solid material that's going to be available to make planets. Far out from the star, the solid material will also be rock and metal because those are still going to condense, but also what we call hydrogen compounds. And these are the things that can form ices, things like water, methane, and ammonia. And so far from the star, you've got rock, metal, and ice forming part of those solid, forming that solid material. Of course, that solid material, what we're talking about to begin with, is just little tiny grains of dust, little snowflakes, if you like, as well. The next step is how do we turn those into a planet? And that process of turning those little bits into planets is what we call accretion. Accretion is just those little pieces colliding with each other and building up to form bigger and bigger solid bodies. And in the inner solar system, since the material is rock and metal, you get solid protoplanets made out of rock and metal. In the outer solar system, you can also make solid protoplanets, but those solid protoplanets are made out of rock, metal, and ice. And they get much bigger in the outer solar system simply because there's more stuff, right? There's all that ice out there. So it's easier to make a much bigger planet than what you have in the inner solar system. And so in the inner solar system, yeah, there's some, those protoplanets start colliding with each other as well, and eventually they produce however many solid planets you have in the inner system. In the outer solar system, those protoplanets go through a second step of growth. So after they get to about 10 times the mass of the Earth, the gas starts to, they start to pull in gas, because remember, there was all that gas sitting around the solar system, all the hydrogen and helium that we've kind of been ignoring up to this point. Well, those bigger protoplanets get big enough they can start pulling in a lot of those gas, and that lets them go from maybe 10 times the mass of the Earth to, in the case of the biggest planets, hundreds of times the mass of the Earth. And that's how you get your Jovian planets formed. And then we have finished up with the cleanup phase, where some of that junk gets thrown, some of the leftover stuff, some of the stuff that didn't go into making planets gets thrown around. Some of it hits planets. We have the heavy bombardment phase there, where planets get lots of craters on them, but you also get a lot of material thrown out into other parts of the solar system to make the giant, to make things like the Oort cloud and the asteroid belt and the Kuiper belt. And this process can even cause some of those giant planets to migrate in closer to their star. And we think that may be why in many exosystems we see giant planets, Jupiter-type planets, hot Jupiters that have gotten really close to their stars. We also talked a little bit about how we measure ages in this part of the course. We looked at the radioactive decay of certain chemical elements like uranium and potassium and so on. And as they decay, they act as a clock that let us measure the age of the rocks that they're in. And so we can use this to figure out when the solar system formed. And it's how, particularly by looking at those oldest rocks in things like meteorites, which come from the asteroid belt, that lets us tell how long the solar system, that lets us tell how long the solar system has been around. And that's where we get that 4.6 billion year age for our solar system. Okay, then we got into the sections on interiors and surfaces. And these two really go pretty closely together, because they're often, because a lot of what happens in the interior is what drives what's going on in the surface. So first of all, with the interiors, we talked about differentiation, how in many planets, if they're hot enough during the formation process, they separate into layers. The dense stuff sinks to the center, the less dense stuff floats outside that. In the very biggest planets, there's also compression, where the center gets squeezed down by the weight of all the stuff over top of it. And that can be a really important thing in these giant planets, because it can change the phase of the hydrogen and helium that makes up so much of their mass. So it turns that hydrogen from a gas, the way we're used to it, into a liquid. and in the biggest planets, even into a liquid metal. And so hydrogen behaving very differently than what we're used to. And so that's why when we say that Jovian planets are, I don't like to call them gas giants because they're not. They're really mostly liquid, even if they're made of hydrogen. But then we talked about heating. And this heating section is one of the most important bits of the course. So many other things come from this. So there are different heat sources, different and in the early solar system, impacts and differentiation both were really important for heating up the interiors of planets. For the terrestrial planets, the current heat source, the thing that's really lasts for billions of years, is radioactive decay. That breakdown of heavy elements actually produces most of the heat that powers the interior of a rocky planet like the Earth. On the other hand, for the Jovians, they're mostly heated by contraction. That is, they're slowly shrinking. And as they do that, that converts a little bit of that gravitational potential energy into heat. And that's what's keeping them so hot inside. And finally, for the moons of the Jovian planets, you have tidal heating. And tidal heating is really big for some of those. In fact, that's the reason some of those Jovian moons are so active. We talked about the ways heat can flow, conduction for really cool interior like the Earth's moon, convection for the warmer planetary interiors. We also mentioned radiation, which is certainly a way heat leaves the surface of a planet, not terribly important in the interiors of planets. If we were studying stars here, that radiation, actually what we call radio diffusion, becomes really important for those. That's their main method of having heat flow in their interiors. But for planets, not such a big deal then. But, and this is the big one, okay? The key thing to get from this is big planets stay hot longer. That's really crucial. And yeah, we'll mention a couple of exceptions here in a few minutes, but that's the thing that's going to drive a lot of what we understand about planets. Is the bigger it is, the hotter it's going to be inside, and that's going to be sort of tell you a lot about what's going to go on in that world. So then we moved into planetary surfaces, and the first thing to remember here, if you are looking at a Jovian planet, you can just skip over anything to deal with surfaces because they don't have them. Remember, Jovians are liquid worlds. There is nothing solid there to stand on. There's no place to put an impact crater. There's no place to put a volcano. It's just not a factor. So you can just, you see a question that's asking about surfaces, and you're dealing with a Jovian planet, you can just say doesn't apply, move on, and you just don't have to worry about that. So then with the worlds that do have solid surfaces, the terrestrials and the Jovian moons, there are four big surface processes: impact cratering, volcanism, tectonics, and erosion. And that order is kind of the order of importance too. Okay, every planet gets hit by things. So impact cratering is going to be a factor on every solid surface in the solar system, even if you can't see the craters anymore. We'll talk about why in a minute. But impact craters are always going to be crucial here. The other thing that's key about impact cratering is that it lets us get a quick estimate on the age of a planetary surface. If you see a surface with a lot of impact craters, that means it's been sitting around for a long time. If there aren't many impact craters, then that means stuff has been happening. Doesn't mean the planet hasn't been hit. They all get hit. But it does mean that something has been erasing those craters. And when you look at the Earth and the Moon, you see a very good example of this. Remember, the Earth's surface has a few craters, a couple of hundred globally, and most of those are buried. The only reason we know about them is because geologists have dug down and found them. The Moon's plastered in impact craters. Okay, it's covered in them. Okay, why? It's not that the moon's getting hit a lot more. It frankly isn't. Instead, it's that the Earth is really good at hiding its impact craters, and the moon isn't. And that comes down, again, to size. And so let's take a look at how that plays out here. Volcanism and tectonics, they often go together, okay? Volcanism, the eruption of material from the interior. Tectonics, stresses, bending, stretching, squeezing the surface. Um, they each produce their own set of features. Volcanism produces volcanoes. It produces big flat lava plains. Tectonics gives you mountain ranges. It gives you big fractures. And I know on the Earth, when we think about tectonics, we tend to think about plates, and we talk about plates a little later on. But remember, plates are not essential for tectonics. So anytime there's stress on the surface of a world, you can have tectonics. It doesn't have to be in the form of plates. Erosion is very much tends to be caused by either the atmosphere or things related to the atmosphere, like liquid water or glaciers moving around on the surface. So erosion wears down the surface. It gives you river valleys, it gives you lakes, it gives you big, once again, flat basins, but in this case, full of sediment, debris that has flown downhill. So all three of those, volcanism, tectonics, and erosion, are going to be more common on solid planets that have that are bigger. The bigger the planet, the more internal heat. That gives you more volcanism, more tectonics. Also, as we'll see more later on, bigger planets are much more likely to have a substantial atmosphere. And so they're going to much more likely to have erosion going on their surface. So size really matters when it comes to planets. The bigger ones really do tend to have a lot more of those surface processes. And those things erase impact craters. So this gets back to why we don't see many impact craters on a geologically active world like the Earth, because the Earth has erased them all. We've gotten hit lots and lots and lots of times, but you can't find most of those craters now because erosion has worn them away, volcanism has buried them, tectonics has removed them completely from the surface. So we can see the surface so we can look at the surface of a world like the Earth and say, there aren't many craters there. It has what we call a geologically young surface. That is, the Earth has been very good at erasing the evidence of its past impacts. We look at the moon, and it has a geologically old surface. Why? Because it's got lots and lots and lots of impact craters. It hasn't done a lot to hide them the way the Earth has. Okay, so we then looked at some examples, and I've talked about some of those. One of the key ones you want to understand is Mars. Mars is the transitional world. Mars is about 1/10 of an Earth mass. And you look at Mars, and it's not like the moon, okay? It's not just completely covered in impact craters. But it's also not like the Earth. It's not geologically active. There's lots of stuff going on there. Mars was active, but it isn't much anymore. Some, but not at nearly the level it once was. And so there's past volcanism, a tiny bit of current one, but not much. There's past tectonics. There's a lot of past erosion and a little bit of current erosion. So Mars is very much on the borderline. Anything that's much smaller than Mars is probably going to be geologically dead, just because it's not won't have had enough internal heat to power much volcanism, to power much tectonics over its history. Okay, you get a world like the moon. Yeah, the moon had a little bit of volcanism early on, not much now. If it's much bigger than Mars, and that could be just two or three times the mass of Mars, that's going to be big enough that it is geologically active, that it's probably it's held on to enough heat to keep geological processes going for billions of years. and not simply die out in the first couple 100 million years of its history. So Mars is your borderline. And so if you're looking at a planet in your mystery solar system table, for example, and you're trying to decide, so is this going to be a geologically active world or not? Compare it to Mars, right? That's that should give you a good sense of which way it's likely to go. We also looked at had a lecture about an extreme example of a small moon that is geologically active, and this was the moon Enceladus. But this is true for many outer solar system moons. Enceladus is just a bit of a poster child for this. Enceladus is a very geologically active world, even though it's tiny. It's about the size of Arizona. Okay, so as a world, it's pretty small, but it has two things going for it. And these two things together have allowed it to stay active, even though it's not very big. And as I say, we see this a lot in those outer solar system moons. One, tidal heating. In those complicated systems of moons where you've got many moons going around the same giant planet. Of course, tidal forces from a giant planet are going to be really big anyways. But that tidal heating can be really efficient at heating those worlds, much more so than, say, the radioactive decay in the Earth. And so that can keep them very geologically active. So we look at, for example, Jupiter's moon Io, and it's the most volcanic world in the solar system. Again, it's around the same size as the Earth's moon, but it's really active because of all that tidal heat. The other thing that many of these worlds have going for them is ice. Ice is, as you know, it's a lot easier to melt ice than it is to melt rock. And so when you think about that from a geologic activity point of view, it doesn't take a lot of heat to get ice flowing, to start melting it, to maybe turn it into water. And so even if there isn't a huge amount of tidal heating in an icy moon, the fact that it's got ice means that it can be it can be active. It can have volcanoes. It can have tectonics, even at very low temperatures. And Enceladus was a classic example of that. But there are again several others around the solar system that are like this, that are worlds that are geologically active, even though they're not very big. And these are all outer solar system moons for the most part. Although maybe some of the small icy worlds of the of the Kuiper Belt, things like Pluto, for example, also appear to have the same kind of thing going on. So then we finished up with the Earth, and we talked about plate tectonics on the Earth. And remember, again, you can have tectonics without plates, but the Earth is kind of unique because it's got plates, and these plates are big chunks of crust that get shifted around on the surface. They get formed in some places and get recycled back into the Earth's interior in others. And so we looked at three different kinds of plate boundaries here. We talked about divergent boundaries. These are places where plates are separating apart and new crust is forming. Generally, that's going to be new ocean crust. And these are usually mid-ocean ridges, right out in the middle of the ocean, although they do crop up occasionally on land to form rift valleys where they split open the crust at in the middle of the continent. We talked about convergent boundaries, and for convergent boundaries, this is where plates are coming together, and what that forms depends a lot on the type of plate that is. If the rocks are in at least one of those plates is oceanic rock, that is basalt, the stuff that forms at the bottom of the ocean, then at a convergent boundary, that material is going to subduct. It's going to sink back down into the mantle. And so you're going to get deep trenches, and you're going to get big volcanoes. If both of the pieces of crust coming together are continental rock, granite, then it's not going to sink because continental rock isn't dense enough. It will keep floating on the mantle. And so instead of going down, it's going to go up and it's going to make really big mountain ranges. When we look at the Himalayas, for example, in Central Asia, that's a continent collision happening right now, and it makes those very big mountain ranges and the big plateau there as well. And finally, we have the transverse boundaries. This is where plates slide past each other. And we're living next to one of those, okay? That's the San Andreas Fault. That's the kind of boundary that gives you the big shallow earthquakes that we're used to here, often quite frequent, and several other features that are tied to the fact that you've got the crust sliding sliding past each other like that. So those are the major topics that we've covered here in the last little while. And so that's what I'm going to be asking about on the exam this week. Remember, this is as an online class, it's always a little bit of a challenge to keep in touch to get all your questions answered. So please, if you have questions, send me an inbox message. Let's meet online. Let's talk about what your questions are. I want you to get these ideas so that we can we can be ready. So you can be ready to do a good job on this. So send me an inbox message. We can meet online. You also so make sure you can come to one of my office hours. Just check the schedule for that. But otherwise, best of luck, and hopefully I'll see you online sometime.